Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's make a start. So we're going to continue looking at different time series examples, just to wrap up all the time series stuff. So what do I want to say about in general? So we're getting quite a few emails about the assignment. This is good, means people are doing it. But I just wanted to, again, reiterate that I can really only be a very limited help when it comes to modelling choices, right? So I'm getting quite a few emails where the email says, well, this is the model I've chosen, what do you think? You'll find out later, right? So I can't really, and the reason I can't really answer those questions is not because I don't want to be helpful. Part of me wants to tell you exactly what to do, but that's the point, right? The point in the assignment is I want you to make those choices. And I get that, when you're doing assessment, you're worried about grades and all that, and you're worried that if you make a bad choice, then your grade will go down. Sure. But I can't take away that choice from you. That's not what we're here to do, right? No point having assessment if I just tell you what to do, okay? So, again, I don't want to discourage anyone from sending me emails, but, just be patient with me when my response isn't, yes, that's right, or no, that's wrong, or whatever, because I'm not going to do that. I'm generally going to say, yes, but that's a modelling choice and I want you to make it, okay? Because we've talked about the general principles of modelling, and that's what I want you to apply, okay? So again, I'm not upset that people send me the emails at all. I just am very limited in what I can respond, okay? All right, we're going to look at a couple more data sets. These are difficult data sets. They're difficult in the sense that they're going to defy analysis a little bit, and some of the choices that probably I should be making when analysing these two data sets are not things we've really talked about too much in class. For instance, I think for one of them a long-run AR model or a moving average model might be a better model. But the reason that I'm going to talk about them is to show you a few things and to show you again that, we're not necessarily going to fit the best model in each case, but we're going to run down a set of choices and try to defend those choices on the basis of what we see and of other evidence that we can get. So there's two data sets we're going to look at initially. They're the questions 1 on tutorials 8 and tutorial 7. There's a third one if we have time we'll have a look at, which is a very famous data set. This first one here is pretty famous as well. It's called the lynx data. So a lynx is a kind of a feral cat. I can show you a picture of a lynx, I guess. It's always good to know what we're talking about, isn't it? So if I type lynx and I go into, there it is. So that's what a lynx looks like. They're cute until you get up close and they'll rip your head off, like most wild animals. It looks kind of like a cat, but it's got these cute little things on its ears, right? So back in the day, many years ago, about 150 years ago really, people in Canada, these were very common in Canada, and Canada gets pretty cold, right? So what are you going to do when it's cold? Wrap yourself in a cat. That's pretty much what the solution was. So they trapped them and killed them and took their skins and used it as clothing, right? These days this is not what we do, right? We buy our clothing at Kmart or better, and it's generally not made of animal, but that's what they used to do. And they used to keep track of how many lynx they trapped. Of course, you know what happens when humans trap animals consistently over many, many years. What happens to the animals? They die out, right? We're not very good at conserving resources, humans, right? You know, we see an animal we want to use, we use it, then they're gone, and we go, oh my God, they're gone. Same thing's happening with things like oil and coal, right? So anyway, this is a really famous data set. It's been analysed pretty much by every person who's ever taught time series because it's such a famous data set. It's annual data, so if I type links on the screen, you can see it starts in 1821, it finishes in 1934. Pretty soon after that, they said we probably shouldn't do this, probably should stop trapping links, so that after that the data changes completely in the sense that there's a structural change. And that raises another point about predictions with time series. There's quite often structural changes that mean prediction based on the past is generally pretty bad. There is an old saying that the worst predictor of the future is the past, but it is the only thing we've got, and so we tend to use it. Okay, so you can see there's definitely cycles in this data. There's definitely cycles in this data. It's annual data, but there's definitely periodic structure, okay? So that's one of the things that for us is going to make it challenging. The frequency of this data as we see it is 1, right? Measured once per year. But you cannot help but see the structure that sits underneath that, right? And you can count the points from peak to peak, right? So we'll start at the second one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So from peak to peak, that's 10, right? So you go 1 through 10 and then you start again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And so on. So it looks like it's got a cycle of around 10, but it varies a little bit. It's 10 or 11, okay? It's not super, it's not as regular as we would probably hope, but it's pretty regular. So that's going to be a feature of the data that we're going to have to think about. And we're also going to have to think about the other things we always think about. You know, is it homoscedastic? What sort of trend should we put through it? All of these questions come up, okay? So it's going to be challenging because, again, it's not simple, right? It doesn't sort of look quadratic and it doesn't sort of look like you can fit a simple model to it, okay? So what do we think? Well, let's go through the steps. Well, first step is it homoscedastic? That's the first question. Is it homoscedastic? That is the variance, is the scale constant? I use my 2 fingers and I move them along. What happens? Do they stay same distance apart? Do they move further apart? Yeah, they probably do moderate a bit. Doesn't seem to be particularly flat. So I think there is some evidence of heteroscedasticity here, right? So what do we do about that? We try different transformations. So we're going to try a couple. We can try square root. So here's the square root transformation. Okay, and I'm just going to go back and forth between the 2 graphs so you can have a look. So you can see that's the original scale. That's the square root scale. So you can see things have improved. It's sort of those big peaks, the 1, 2, 3 big peaks, have kind of come back to the field a bit. It's better. Is it good enough? That's the question. We could try log. And log kind of might be too strong. Log kind of pops some troughs down out the bottom, these 2 here. But the peaks are now under control. The ones that are up high are now under control. Okay? We could try things like cube root transformations, which is in between square root and log. Why not? We'll have a look and see what we think. So instead of log links, we'd use links to the power 1/3. That'd be a cube root. Links to the power 1/3. Okay, and it looks in between square root and log. Those big peaks are still there, and you can see the troughs at the bottom have started to pop down. Okay? So none of these 3 seem to work perfectly. Square root tends to maybe not quite bring the variance down enough. Log tends to be too strong, tends to pop stuff out the bottom, and cube root kind of does a bit of both, but not really enough of either. So it's a good question what to do from here. Now, it turns out, like I said, this is a famous data set. It's been analysed hell, west and crooked by just about anybody who's ever studied time series. The usual transformation people use is square root. And the reason they use square root is for a completely separate rationale. They use it because people think that perhaps length trappings are a Poisson process and square root is the canonical transformation for a Poisson variable. That's the reason that's typically given for using a square root transformation. Again, it's a choice, right? Remember, and this is something that you get by the end of this, by the end of today at least, you'll be so sick of me saying, you've got these choices, none of them are right, some of them are better than others, probably some are wrong, and you've just got to make the best you can of it. So, you choose, okay? The rationale for any of the three choices would simply be to stabilise the variance, okay? But as the solution here says, it's hard to choose between them. And the classical approach is to use square root. So we're going to use square root for that reason, and we'll see how we go, okay? Now, the other thing we need to think about is trend and seasonal. Now, I can't use STL. And the reason I can't use STL is the frequency of the series is 1, and it'll just refuse to fit, right? You can try, right? If you try to use STL, I'll do it here, H equals STL of lengths. I won't even bother with S dot, what is it, S dot window equals periodic, might as well bother. T dot window equals 50, that'll do. Doesn't much matter. It's just going to give me an error anyway, right? So series is not periodic or has less than 2 periods. In other words, frequency is 1. That's R's way of telling you that the frequency is 1. I could be a little bit cheeky. I could say, well, let's recreate lengths. I'm going to create a new object called lengths 2, which is a time series that contains the values in lengths, but which manually sets a frequency. And you probably want to do frequency as 10. Again, you probably want to count from peak to peak just to make sure that's about right. I think it's 10 or 11. Let's see what happens with frequency equals 10. Okay, now if I do this and I use STL, I can go STL of lengths 2. It'll do it. If I plot H, I'll get an STL output. Okay. I think I've undersmoothed the trend bit, right? Look at that trend bit, looks all over the place. So T dot window is 50 is probably a little bit small. How much data do I have? I have from what, 1821 up until 1934, that's over 100 years. I probably should have gone bigger than 50. Let's try 80, see if it improves matters. A little bit. 100. Yeah, it's probably about as good as we're going to get. Okay, so you can see what's it doing. It's saying, there's my original series, okay. You'll notice that's on the original scale, so I should have been a little bit more careful again. Instead of using lengths 2 here, I should have used square root of lengths 2 if that's the series that I'm going to be playing with. So let's do that. Okay. So there's the top panel, of course, is the original data, square rooted, right? So you can see it looks fairly variance stable. There's my seasonal component. Now, just want you to notice something about this. It's not quite right, because what we should see, if you move along that second panel, the peaks in that second panel should match up with the peaks in the first one, and they don't. They drift a little bit, right? See how it seems to be going okay initially, and then by the end you can see you're just out by a few, right? So it's not quite right. 10's not quite right. So I might go back and try 11. And again, this is just messing around, trying to see if I can work out what periodic series is going to work for me, okay? That looks a little bit better in terms of the way the peaks match up. Not perfect, but a little bit better. And the reason for this is that the periodic behaviour is not quite regular enough. Generally speaking, it'll repeat either every 10 or 11 points, but it varies just a little bit. People who follow predator-prey models would notice that this is a pattern that occurs in predator-prey relationships. And the reason it can get out by a year is because of climate factors. So, for instance, if you have a very cold year, for example, it can just shift things along a little bit. So that can happen. But that might be better. We'll try this. Now the trend, look at the trend there. You can see maybe we could fit a quadratic. Again, I just want to point out that, you know, you've got this issue where the scale of your trend is really small compared to the scale of the data, right? So again, even though that looks like there's a big curve to it, you might be better off fitting a flat term, okay? But we can try that. And here's my irregular component. Now have a look at my irregular component. What do you see? What do you see? It looks a little bit too regular for me, right? Notice how you've got bunch of ups, bunch of downs, bunch of ups, bunch of downs, right? Genuinely irregular data probably wouldn't do that. It looks a little bit too regular, and that's probably another sign that I've got my frequency wrong, okay? So this data set presents a challenge. You've got what looks like periodic behaviour, right? When you look at this with the naked eye, you go, yeah, look, this thing's going up and down every, so many years. Then when you try to pin down that number of years, you immediately run into trouble that it's not as constant as you would like it to be. Okay? So that's a challenge for our modelling. You could fit a quadratic, maybe try that, see how you go, and we'll proceed. Now, so let's try a few things, okay? So let's first of all consider the trend. Let's think that a quadratic trend might be the right thing to do. So I'm going to go back to looking at the original links data. I'm going to go mod 1 equals lm links tilde time of links plus time of links squared. Okay? So mod 1, there's the model that gets fit. What happens? It refuses to fit the square term. Okay? Refuses to fit the square term. The reason it does that is because it thinks these two are collinear. We could try centering time. So let's let x equal time of links minus, what's a middle year? 1821 to 1934, 1880. That was a good year. Okay, and let's refit with x plus x squared. See how we go there. Okay, again, it's refusing to fit that second term. Maybe it's having trouble with calculating x squared. It's another trick you try. And now it'll do it. Okay. So, what did I do there? Sometimes when you fit a square term, it actually requires you to calculate the squares first. That's what I does in R. So I of x squared actually calculates them first before it puts them in the model. Okay? This sometimes happens in R when you've got a model formula involving powers of a variable. It refuses to fit it. There's one or two reasons that happens. It either thinks they're collinear or it's refusing to actually conduct the calculation internal to the model fit. So you can force that by using the I function. So there we go. We've gone ahead and fit it. All right, let's have a look at the summary of mod 1. You can see square terms not significant, linear terms not significant, right? So all that effort And it looks like we probably don't need those two terms. So even though the STL output said down and then up, right, it showed you that sort of curvature, remember that the scale on the graph is such that that's very shallow. It's really very shallow. And so that's suggesting we just fit a flat line. Okay? So where does that flat line sit? It's the mean of square root lengths. Have I been using the square root? I haven't. Oh dear. Why does nobody stop me being stupid? That's what you guys are here for. Oh no, you're here to learn, that's right. You're here to learn. Let's do that again. You can see it doesn't change anything, I just forgot to take the square root. Okay, so we're not going to fit a quadratic trend or a linear trend, we're going to fit a flat trend that is at the mean of square root of lengths. Okay, so what's my model so far? So far we've got square root of lengths equals 34.0623 plus whatever else we want to fit. Okay, so plus seasonal plus xt, where xt is my irregular. So we're up to so far. Now, you'd already be guessing that, and this is worth thinking about, when you fit a flat trend, what you're essentially saying is that the series isn't going anywhere. And that has a real impact on prediction, right? You are going to predict every year, 34 for the square root of lengths, going forward, right? Is that a good prediction or a bad prediction? Well, if you believe that there's no trend, it's as good as you can do until you start dealing with the seasonal, okay? And we may not be able to deal with the seasonal because it may be too irregular for us. So that could be problematic. So we're going to try a couple of things. Let's try and fit a seasonal, okay? See how we go. We'll have a look at the residuals and see whether we've done well or not. I'm going to try and fit a seasonal of size 11. So the length of links, the length of links is, we've got 114 data points, okay? 114 divided by 11 is, it's easy math. What do I have to do it? 10, all right. How many peaks do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got 11 peaks. So 111 divided by 11 is 10. I should have 10 peaks. I've got 11 peaks. Okay. What if I tried 10 as my... What's 111? What's 114 divided by 10? You guys are hopeless. It's 11.4. Yeah, all right. Okay, 1, 2, 3, 4. I feel like I'm alone here today. So sad. 1, 2, 3, 4. I suppose if I'm alone here, I can just count and no one cares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.4. That's about right, isn't it? Okay. So I'm going to try frequency 10, see how I go. So, V is going to be a factor. And it's going to be the numbers 1 through 10 repeated 11 times. What's 10 times 11? 110, thank you. So C, I didn't put my rep in. I need to repeat 1 to 10 11 times, okay. And then I've got 4 left, right? 1, 2, 3, 4. So there's my, and I've left out a bracket. There's my factor, all right, let's fit it. Mod 2, this is my attempt at a seasonal model, equals Lm, square root of lengths, till the, now I've got no trend, so I'm just going to let the constant deal with that, till the V. Okay, goes ahead and it fits it, I've got the right number of things, all right. Let's have a look at mod 2. So there's my model. It says that the intercept's 20, right? Then in the second year of the cycle, I'm at 3. In the third year of the cycle, I'm at 13, and so on, right? So remember, baseline, first year of the cycle, I just get that. Then in the second year of the cycle, I add that. In the third year of the cycle, I add that. Fourth year, that. Fifth, sixth, seventh, eighth, ninth, 10th. And you can see, you know, this series starts low, then gets higher, 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 drops, 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 drops. Okay? So I'm going to get that characteristic bouncing around that you see with the wiggles. Okay? All right, let's plot time of links versus square root of links. Let's do that. Type equals B. We'll make a type equals L actually. The dots are just going to get in the way. Colour equals blue. Okay. Yuck. I said type equals L, but anyway, it's ignoring me. All right, fine. PCH equals 1. What the? Why on earth is it doing that? Anyone know why it's doing that? Oh, sorry, I forgot I'm alone here today. LTY equals 1. Let's see if this works. That's what it wants to do. Sometimes R just does very strange stuff. That's what I wanted. Okay. So how did I do that? Well, it was the reason, for some reason, it had decided that time of links had a structure. I think it was treating it as a time series object instead of just as a vector. So I've told it to be a vector. Okay. As dot vector. So, okay, and then I'm going to go lines as dot vector time of links. Comma fitted for mod 2. But they'll make this one red. Colour equals red. Type equals L again. Okay? So this is a superimposition of the original data in the blue, okay, followed by my fitted model in the red. And you can see, does okay, although there's some problems. Okay? Initially, it seems a bit out of sync, then it gets into sync. So this suggests to me that something happened, probably around in the middle of the data, where the actual length of each period changed, probably from 10 to 11. So I'm not going to try and accommodate that, it's just too much of a pain in the backside, but you can sort of see we're doing okay with this model. It's not dreadful, but it's not systematically great either. Okay. Let's plot the residuals from model 2. Mod 2 type equals L. These are the things that should have very little structure left. They should just have the dependent part. And you can see, well, it doesn't look great. This thing still seems to be wiggling far too much, and the wiggling seems far too regular for me. It's not particularly regular. If you count from peak to peak, you get different numbers all over the shop. So we could treat this as irregular and proceed, okay, which I think is our choice at the moment, and see how we go. So let's have a look at the Box-Jenkins identification for the residuals for mod 2, which is our model to date. And you can see stuff happens. So, stuff number one, the ACF. What's going on with that? Probably non-stationary, right? So, well, again, it's got this structure where it's definitely getting smaller in size, but it's getting smaller very slowly. By the time you're off the end, probably the next cycle's going to go in and stay in. So again, it's probably borderline stationary, so we have choices to make. Aren't you glad this wasn't the assignment question? Anyway, the PACF says fit 1, 2, and then probably you'd ignore the rest. Probably says an AR2. Okay? So again, our general rule is we look at the ACF and we go, is the series stationary? Okay? This case, maybe not. So think about that. If we were to go ahead and fit a model, 1, 2, clear spikes outside, everything else not clearly outside, I'd probably go with an AR2. So our choice at the moment looks like seasonal trend with period 10, okay, followed by an AR2, and then hope that the residuals are stationary. Okay, so let's fit that AR2. So fit AR equals rake of residuals of mod 2. Okay, wait a respectful period, then fit AR dollars coef, comma 2. So the AR2 model would look like xt equals 1.22 times xt minus 1 minus 0.59 times xt minus 2. Okay? But the proof's in the pudding. Ident of fit AR dollars residuals, second column. Oh, why is it not happy? Residual. Yeah. Resid, sorry. What fun. Okay. This is all right. This is all right. The ACF's back under control. Okay. So again, we've got this feature where it was borderline stationary, right? Probably damping down too slow, but it's getting there. You fit the model and the structure all sorts itself out. Okay? The PACF's got nothing left. You can see, touches the line, but we don't care. Pretty much everything's within the train tracks. Okay? So it's all good. And so we've got a model. That's model 1, right? First choice. So model 1 is going to have this periodic component of size 10, followed by an AR2, and then you've got no structure left. So that's choice 1. All right. What else could we do? Well, we've got two other options to track down. The first option to track down is to say, look, I wasn't happy with the ACF in that first attempt, right? It looked like it was going down too slowly. So maybe I'll try differencing, okay? So why don't we think about an analysis for the difference data? At least have a look at it. So let's have a look at a plot of diff of square root links and make it fill the whole page. So, okay. That's diff of square root links. Again, it looks pretty wiggly. Doesn't look quite as regular as the other one, does it? Doesn't look quite as regular as the other one. It's definitely got peaks and troughs, and I guess if we counted points, which we can do, comma type equals B, PCH equals 16. Okay, if we count from peak to peak, what do we get? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's go over here. 1, 2, I don't know where the top is. Let's go over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. My God, it's all over the place. right? Doesn't look nearly as regular. If I count from peak to peak, I get numbers like 9, I get numbers like 13. I probably can't fit a seasonal to this and have any hope that it's going to work. So that would mean no seasonal. That means I have to treat the whole thing as irregular, because I don't think there's a trend in this, right? This looks flat. I mean, and certainly if the original series was flat, the different series had better be flat, right? So, no trend, no seasonal, good to go. Let's do a Box-Jenkins identification. Ident of diff of square root links minus the mean of diff of square root links. That's what I get. Now, let me explain what I did there. I fit it because I decided there's no trend, no seasonal. All I'm doing is fitting a mean, right, to the differences. So the residuals are the difference series minus the mean of the difference series. Right? So I didn't want to go through fitting a model using LM and all that sort of nonsense. I just wanted to do it. So there we go. What do we see? Same problem. Right? The difference series did not resolve the stationarity problem. In fact, it might have got even a bit worse. Right? Because this thing, it doesn't look like it's going down to 0 even quite as fast, does it? Okay? Doesn't look like it's going down to 0 even quite as fast. Look at the PACF. Spike, 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 spike. Then the rest is okay. This is saying fit 1, 2, 3, 4, 5, 6, 7. Fit an AR7. Are they nuts? No, they're nuts, right? That's just silly. So that didn't really produce an outcome for us that is going to lead to any sort of satisfactory model. Okay? I told you this data set was a bugger. The truth is you probably shouldn't be fitting AR models to it, but anyway, we're doing the best we can, right? All right, so Model 2, which was looking at the difference series in the hope of resolving the stationarity problem, epic fail. Okay, and that happens with modelling. Sometimes your modelling leads you down a path and you get to the end and there's nothing. Okay, so what's our third option? We have a third option. The third option is to say, okay, we have one satisfactory model, which is to fit this seasonal of length 10 plus an AR2, but we have some concern that those seasons aren't regular enough. So what we could do is treat the whole thing as irregular and see how we go. Okay? And that's the final thing we'll look at. How do I do that? Well, if I'm going to treat the whole thing as irregular, I'm going to be doing a Box-Jenkins identification of the square root of lengths minus the mean of the square root of lengths. Right? In other words, I'm just going to fit a flat line to the whole lot. And you can see, same sort of things are happening. Slow decay of the ACF, which means probably not stationary, followed by an AR2. Now, this is really interesting, right? Because we went ahead and we fit this periodic thing in the hope of catching all of those peaks and troughs. And the ACF and the PACF are not telling us a different story. It may be that fitting all that structure didn't really help us. Okay? If I go ahead now and fit an AR2 to this, and all the structure disappears, I've got a candidate model. So let's give that a go. So let's go fit AR, a rake of that thing, square root lengths minus the mean. So this is my new series. Okay, boom. Wait, oh, it's going to pump it to the screen. I meant to go fit AR equals that. Okay. Wait, there it is. Fit AR, dollars, coef, second column. So I get coefficients which look like 1.306 and minus 0.688. So xt is 1.3 times xt minus 1 minus 0.688 xt minus 2. And now, the moment of truth, ident of fit AR dollars resid, second column. And you can see the ACF now behaves itself. And the PACF shows nada, right? Nothing going on here. Ignore that, ignore that. Well, you kind of have to, right? You kind of have to. Again, I want you to get used to the idea that the way to think of this, here's a neat way to think of it. And you will understand this because I'm a cyclist, right? So this is the road, right? That's the road, yeah? Okay? But if you're a cyclist, you ride out here sometimes, and you ride out here sometimes. You don't ride out here, or way the hell up there, because that's in the bush, right? As long as you're close enough to the road, it's all good. You're still moving down the tracks. So what we're looking for here is structure, and generally speaking, you don't want to over-interpret spikes that are close to the line, right? And again, we talked yesterday about why that is. There's that multiple testing problem. There's the issue that the bounds, the edges of the road are based on large sample theory. And we never have really large samples. We've only got 114 data points here. So think of the edges of the road as being, you know, the road plus a bit of shoulder. So you have a little bit of leeway to make choices, okay? And remember, one of the things you always want to do is choose small models where you can. Small models that fit adequately are way better than large models that fit super well, because super well generally means overfitting. And so small is better. So try and use that as a guiding principle. And so we've ended up with a really simple model. And the really simple model says that the best you can probably do with this data is to say the square root of lengths is a constant plus an error which has dependence, which is modelled as an AR2. Prediction based on this modelling would only predict the square root of lengths to be a constant forevermore. Now, this will not sit well with people who look at that initial graph. When you look at the initial graph, you are seduced by the wiggles. And you think to yourself, surely I should be able to predict better than just a flat line. And there's a reason that you can't. And that reason is that those wiggles are not nearly as regular as you thought they would be. When you look at that initial graph, you think this is repeating every single 10 years or whatever. It's not. It's varying. It's sometimes 10 years, it's sometimes 11 years. Okay? That destroys your capacity to predict. So, because you don't know which cycle you're in and you don't know where in the cycle you are. And so your better prediction is to go with a simpler model. Okay? And so that's the links data. So that's a really challenging data set. And it's challenging for a couple of reasons for us. Those reasons are that we've really only brushed the surface of time series modelling. So we've restricted ourselves to AR models. Because of that, this data is hard to analyse. Okay? Also, we can only analyse data that's measured particularly regularly. Okay? Cycles have to be regular. If you're fitting a seasonal, and the answer to the question is the pattern regular? No, then you are doing the wrong thing. Okay? Seasonal means regular. You know how every week Saturday occurs on the 7th day? Yeah? It's not like sometimes it's Sunday. No, it's Saturday, right? That's what regular means. It doesn't mean you wake up, oh, maybe it's Tuesday. No. If it's the 7th day, it's Saturday, yeah? You can stay in bed. I don't know, you work on Saturdays maybe? I don't know. I never stay in bed, I have to tell you the truth. I always get up, but anyway. Call me crazy. So, that's the links data. All right. Boy, we used a lot of time on that, but it's such a tough data set to analyse. All right, let's have a very quick look. Should we have a quick look or should we just say that's enough? You guys have probably seen enough time series now. You're probably sick of it. And there's only 4 minutes left, so there is just no chance I'm going to get very far with the data set. So there's one more data set in the tutorial stuff. I'd recommend you have a look at it. It's a bit tough too, it's got similar problems. The other data set I was going to show you is the sunspot data, very famous data set. Sunspot. Oh, what's it called? WSUN. WSUN. It's built into R and it's called WSUN. Plot. The W. Oh, I hate R. There we go. Get rid of that. Try again. There's the sunspot data. It's got, again, the data sets that I'm showing you now are interesting because of the fact that we struggle to analyse them given what we've learned. So this is annual data as well. By the way, the sunspot data is measured. The data set that's built into R is measured between about the mid-1750s, mid-1700s and about 1900. Of course, they continue to measure sunspot. You can actually go onto NASA website and download the data from when they started to today. Right, they measure sunspot stuff very regularly. Does anyone know what happened this year with sunspots? Did you follow the news? Why not? Such interesting stuff. This year there was a period during the year where there were no sunspots. People got very worried. They thought something bad was going to happen. Didn't. But anyway, it's all good. Okay, so again, look at this. You can see it's got that regular structure. Okay? It's worth playing with this data. It's got a few features that are going to cause problems. For instance, the period of this thing isn't as close to uniform as you would hope. It's got a lot of the same problems as the links data, frankly, and transforming it doesn't seem to be a particularly easy thing to do to get it to work. And then you have this sort of period here between 1860 and 1880 where, well, honestly, weird stuff happened, right? So, anyway, good fun to look at. Okay, so here's the good news. There's good news and then there's more good news. So let me tell you both of them. The good news is, the first piece of good news is that we've now covered all of the lecture notes, right? And you probably go to yourself, well, hang on, there's 2 weeks left. Why did you finish so early? And the answer is because you guys have to do your assessment, right? No exam, so I had to cover everything before you did it. So that's by design. Now, so that's good news number 1. Good news number 2, we're not stopping. We're not stopping. Or is that bad news? I don't know. So we've got 2 more weeks of lectures. That's 6 hours you can dependably spend with me. And I'm going to come along and I'm going to talk about stuff. So what stuff am I going to talk about? Well, on Monday I'm going to talk about general things about statistical graphics. If you've watched my YouTube video, you might have seen the sorts of things I'm going to talk about, but it won't be word for word the same because I'm hopeless at repeating stuff. So that'll be Monday. Tuesday, we're going to talk about Ed Tufte and we're going to go through some of the examples out of Tufte's book. Okay? Then on Wednesday, we're going to look at all sorts of examples of good and bad graphics. Okay? And we're going to talk through what's good about them, what's bad about them, those kinds of things. Okay? So that's what next week's going to look like. So no new statistics, probably, so you can relax. I want you to, and look, this has been true of every lecture we've had so far anyway, right? If you want to come, you come. If you don't want to come, you don't come. Right? That's fine. I hope you'll want to come to next week's because it'll actually be more fun and there's no pressure in terms of if I don't learn something today, I don't know, someone will hit me or whatever. So it's mainly designed to kind of round us off and talk about interesting things. The following week, I'm going to go through more examples of good and bad graphics as we wind towards the end of the assessment. But for the last lecture, at least, I'm going to do something that's just not statistics. It's just going to be fun, okay? And you just have to wait and see what that's going to be. And if you don't show up, your problem, okay? So you've got everything you need to do all the assessment now, okay? So get to that. Please come along for the next couple of weeks because we are going to keep going and it's going to be fun. More fun than we've had even up till now because I know everyone tells me how much fun it is. And I'll see you then. Let me just put this away before I forget.